All right, guys, I'm going to get started. I think it's 9:30. So I got a few emails about the upcoming exam. So we've got our first exam is a week, basically 2 weeks from today. It's going to be our first exam. The syllabus says the focus is going to be on everything that we've already covered. I think that's effectively what we're going to do, except that what I would like you guys, I'll put up an example of something I'd like you guys to be able to do, and hopefully it'll make sense once we get to, I think, some of these other aspects of this chapter that we're going to cover right now, which revolves around drawing transition states and diastereoselectivity selectivity, and I think more complex reactions. And so last class, this is one of the things that so basically these next two things, I'm going to want you to be able to sort of explain and think about on the upcoming exam. And the first is kind of what we discussed last week. And that's that when you have sort of conjugated systems, whatever that conjugated system is, right, here's a triene. Last week we discussed things like dienes and alkenes. And I think for this upcoming exam, what I would like you guys to be able to do with a question like this is identify the molecular orbitals that are involved with, say, the HOMO or LUMOs. And then furthermore, I want you to sort of think about coupling reactions that involve these and how we may have these matches. So for example, why does the Diels-Alder reaction work? Identifying the HOMO of one, identifying the LUMO of the other, and seeing how this would work. And so a molecule like this, if I were to give you, say, for example, this triene, I would expect you to be able to identify the sort of HOMO-LUMO orbitals of the system. And so again, what we would have here, right, is how would we start this, right? We would have to sort of draw at the very beginning orbitals associated with each p orbital in this compound, right? And so how many, effectively, atoms are on here that have p orbitals? 6, right? So we have 1, 2, 3, 4, 5, 6. Okay, and so one of the first things that you'll often do, right, is think about the fact that what are we doing? Well, we're filling a system that looks something like this, right? So for each carbon, there is a p orbital associated with that, right? And it's those 6 p orbitals that come from each of those carbons that are involved in the sort of overall picture of the molecular orbital diagram, okay? Now, once you start getting to larger numbers, you can do just what we did before, and you can certainly fill from the ground up. Sometimes that can take a little bit of time as well. But if you sort of start to identify the question of how many possible when we start to think about how many different molecular orbitals would comprise this, right? In the case of, say, for example, the alkene, right? When we were looking at just the molecular orbitals of an alkene, right? Right? How many different molecular orbitals do we have? 2, right? So we have, right? So we have the sort of, right? So we had the HOMO and we had the LUMO. And it became pretty apparent, right? So our 2 electrons would be here. This one would be empty, so this would be our LUMO, right? And when we had, say, for example, a diene, right? You guys remember how many were associated with the diene? 4. Right? So if I give you sort of 6, you would assume that there's how many? 6, right? And so what that sort of tells you is you don't necessarily have to fill out all of them, right? Because in the case of each of these systems, right, yeah, we need to see both of these here, but we really need to only go up until we're full. And so as I start making these diagrams, right, you sort of recognize that in each of these cases, it's basically the halfway point, right, is where it sort of splits off. So in the case of a diene, right, it's sort of, this one is the HOMO and this one is the LUMO, but in the case of the, sorry, in the case of the alkene, but in the case of the diene, right, it was, the second was the sort of HOMO, the third was the LUMO, so it's that sort of halfway point. In the case of this, and again, we can do that just by thinking about how many electrons are involved in this system, right? And there's how many electrons here? There's 6, right, involved in that pi orbital. So we fill up 2 at a time. So you can think about it that way as well. And so if we're filling up 2 at a time, how high are we going to go? We're only going to go up 3, right? And then the 4th will be our LUMO. So we really only have to go up to the 4th in this case. Right? And we know that the first one has no nodes, right? So that's the one that's going to be all in the same phase. And it gets to the point where, just saving chalk, I can almost ignore the middle ones because it's oftentimes the exterior that we care about. Right? The second one is going to be one node, right? And that node is going to be halfway in between, right? So we can sort of think about a system like this. Right? Again, we're going to be filled on that side, and this side will be filled. Right? And then we move to the next one, right? We're going to have 2 nodes, right? And that's going to be, again, sort of dealing with symmetry here. So the endpoints, right? So it's the endpoints. And again, there's this sort of back and forth, right? That you notice the pattern. When you look at the ends, both on the same side, opposite side, same side. So again, as you sort of continue that trend, you'll see that sort of continues. All right, we're now opposite. Oops. Right, so that are sort of, we sort of switch back and forth, right? Same side, opposite side, same side, opposite side. And again, we have 6 electrons, so this one's going to be full, but this one's going to be empty, right? And so I expect you guys to be able to draw a molecular orbital diagram in this sort of way, where you can start filling up the nodes, and then you can identify the HOMO and LUMO, right? And so the HOMO is going to be this one, and this one's going to be the LUMO. So I want you guys to be able to answer a question similar to this, you know, where I give you something that where we have some certain number, but then I'd like you to also be able to take it to the next sort of stage. I could throw up some hypothetical reaction, right? Take it one step further. And I feel like I'm at least leaning towards asking a question like this, but I can't promise that I won't change my mind. But prepare for a question like this where you may see, you know, asking the question, could this reaction take place, right? Where I sort of ask, is this a reaction that could take place thermally? Or if I gave you guys these 2 molecules and said 2 things could happen, right? One of these 2, right? The question would be which one of these 2 would likely take place, right? And subsequently show the examples of the molecular orbitals that would show whether 6 plus 2 would work or whether 4 plus 2. And again, if you're paying attention to the Diels-Alder reaction, you know that one works thermally. You know that 4 plus 2. You should know this, but I would like you to be able to explain it using a molecular orbital diagram explanation. So here's a sort of, I guess, an exam practice problem for you guys. So thinking about that, and perhaps we can go over it during the review class. I see a hand that looks like it's up. Yeah.
Well, I don't understand how we can go over the orbital diagram. I know it takes information and count the number of phase changes, and you keep the number, and it works and it's allowed. But if it's an odd number, then it's a completely reaction.
Yeah, well, I. Say it again?
It's sort of like the diagram that we are showing. How do I explain whether or not the reaction is allowed?
Yeah. So go back and rewatch my video. but I'll just sort of explain it again, just sort of very briefly. And that's in a situation where you fill up the pi orbitals, right? It's sort of I sort of explained it as a wave function, right? And so if you have, I want to get to other stuff. But if you identify, say for example, the HOMO of this with the LUMO of this, the LUMO of this is going to be this, right, where this is sort of a wave function, if you will, with one sort of node in it. Right, if you remember this one, this one is sort of a node this way. And if you notice, it's sort of a continuation right on the bottom. Again, this isn't the best description of it, but the way that I try to explain it to you is from sort of a wave function theory. So the way that you classically hear, I think this is the way that at least makes sense for me. The way that people will often sort of explain it in organic chemistry is these are on the same face, right? These are on the same face. It's a match. So yeah, I mean, you could sort of think about it that way. I'm not expecting you guys to really understand the mathematics behind it, but rather understand this theory, because it ends up applying to a lot more chemistry beyond what you guys have seen here. There's a lot of reactions, such as we're going to be talking about a lot of pericyclic reactions. There are a lot of stereochemical processes which you don't necessarily have to understand, Schrodinger equation to be able to sort of figure this out. But this sort of tool of identifying the HOMO, identifying the LUMO, look where these sort of map over. Because this carbon is forming a bond with this carbon, right? And so if you think about it, where that wave function is, it's closer in proximity, right? And where that wave function over here is, it's closer in proximity, right? So the nodes down here match on this carbon, and the nodes over, or sorry, not, excuse me, I'm saying nodes. The molecular orbital, if you will, sort of matches on this side, right? So you have these both are identical on this side, and these are both identical on this side. And it's that ability to sort of recognize how it matches. And again, we explained it in terms of how a diene wouldn't work because it doesn't match. So go back and rewatch that video, and if you're still confused, we can talk about it during the review class. But that's, that's the extent that I expect you guys to be able to do it, is look at the molecular orbitals, see that this matches, where the two carbon-carbon bonds are forming. And that's what's going to tell you. And again, it's simply a tool to rationalize a lot of chemical behavior. Okay? All right, so again, here's your sort of pre-review question. Now we'll get back into Diels-Alder a little bit later. You guys know the Diels-Alder. I want you to be able to know what a Diels-Alder is. What I'm not going to hold you guys responsible for this exam is aspects of stereochemistry involving Diels-Alders, but we'll discuss it in the next few classes. So I'm going to discuss that later on today, diastereoselectivity. selectivity. But it takes a little bit more time and practice, and I'd like you to focus. That's going to be, I think, for exam 2. But what I would like you guys to also be able to start thinking about is, again, reactions that we've seen in the past. But now put in a slightly different context. And this is aspects where we have dienes, right? And we can do a lot of, we've had an entire chapter, right, in Organic 1 that was devoted to reactions of alkenes. And one of the sort of points that this chapter makes, in a way, is that dienes can do a lot of the same chemistry that alkenes do, but there is perhaps a predictive difference in these based upon sort of resonance forms, right? So we discussed last week how if you take a molecule such as the one that I've shown you here, right, and I treat it with some type of acid, right, we sort of ask the question, all right, where might this alkene protonate, right? And for a couple different reasons, we sort of said that the external proton is is going to be the one that's going to pick up that hydrogen, sorry, the external carbon. This carbon is going to be the one that's going to pick up the proton, again, leaving behind the carbocation. This would be predicted even without a resonance argument, right? This is based upon, you guys sort of learned about Markovnikov addition across the alkenes and how the more stable cation resulting from that protonation is the one that will end up reacting. But there's also this factor of sort of resonance in dienes. All right, and so you have situations like this, where now you sort of move that diene over, and that provides a little bit of sort of greater sort of resonance to this general overall system, right? And now when we look at these two cations, this sort of comes to the second point, and that's that you still have the bromide, right, left behind from this reaction. Right? And that bromide can in principle react with either one of these carbocations, right? And so when we draw this resonance form, right, resonance forms are simply indicative of the the molecule doesn't look like this, it doesn't look like this, right? It's somewhere halfway in between. Perhaps a better description of these molecules might be something like that, right? Where the electrons are shared between the two. But when you look at the two resonance forms, what you also notice is that you have sort of this shared delta positive here, and you've got this shared delta positive here, and so that bromide can in principle react with either of those positions. And the book chooses to use this type of reaction. I think it does it with bromine, for example, but you could really think about this with a variety of different alkene reactions to really discuss products that would arise through what we call kinetic control versus thermodynamic control. And I'm not sure that it's the best description of thermodynamic versus kinetic control, in part because I think some of the governing factors behind why it goes one way or the other, you would perhaps need some type of computational understanding of it, but at least at a rudimentary level, we could reason this based upon based upon these sort of principles. So let's think about the products that would form in both these cases, right? Okay. So in the case we have sort of two products of this reaction. One of them has the bromide on a secondary carbon. The other one has the bromide on the primary carbon. And in the case of the alkenes, one of them has what we would call sort of mono-substituted alkene, right? The other one we have what would be called di-substituted alkene. So let's just, before I sort of ask this next question, let me ask this question. Okay, so for you guys, what does it mean? I mean, when I say thermodynamic control, how many of you guys, when you hear that, you immediately know what it means? How many of you don't really know what it means? It's okay to be honest. Okay, so this idea of thermodynamic control, somebody that knows what it means, tell me. Yeah. Yeah, the lowest energy product, exactly. So it's the one that's going to form, you let it go for forever, right, at as high a temperature as you can, and whenever that product that forms is the most stable, that's what we consider the thermodynamic product. So it's the most stable product. Okay, so this is sort of overall stability. And that's in contrast to kinetics, which is what? Yeah. Yeah, it's the one that sort of happens the fastest. Okay. And so sometimes you guys will see sort of the energy diagrams that kind of explain this, right? Because The kinetic product is the one that happens the fastest, so usually it's the one that has the lowest barrier to formation. We talked a little bit about Wittig olefenation. Maybe perhaps we could revisit Wittig in a moment to perhaps better explain Wittig. But when we think about the possibility of some reaction, right, we have a sort of a transition state here, right, and we look at this would just be a sort of a reaction, so if we just say reactive intermediate, and we have, say, product A, product B, right, you'll notice that the reaction to go to product B, for example, is higher in energy, right? It's going to take more energy to get over that barrier, but the overall product is lower, right? So if you have enough energy in this system, you're going to get the thermodynamic reaction. If you let the reaction go long enough, eventually everything will go back and forth and we'll eventually be able to go over this barrier and will lead to what we call the thermodynamic product. However, if you let it go shorter, where you don't allow it to have the energy to go over this transition state, or you don't let it to go and react long enough, then what you might only see is the sort of kinetic product, which I've shown is this. So in this instance, again, these are just terms that, you know, certainly in more complicated aspects, sometimes it's difficult to identify kinetic or thermodynamic product, but this is probably the simplest as possible diagram that sort of illustrates that. So the product A in this case would be the kinetic, because it's the one that's going to form the fastest. Product B would be the thermodynamic. And this just happens to be one instance where the thermodynamic product and the kinetic product are different. But certainly there are instances where the lowest energy product could also be the fastest one to form. And so it's not necessarily an either or, right? Is it the quickest one to form? Then it's the kinetic. Is it the lowest energy that could possibly form? It's the thermodynamic. And sometimes both of those, it could be the fastest to form and it can be the lowest energy. So that would be the case as well. So again, it's not an either or. But when you look at these two products, right, perhaps from the standpoint of identifying the thermodynamic product, we may be able to, using the rationale that perhaps we've learned through Organic 1, we might be able to predict which one of these might actually be the lower in energy overall product. Does anybody want to take a stab at it? Yeah. So I've got to vote for the lower one. How many of you guys think the lower one's the most stable? How many of you aren't sure? So why do you think this one's the lowest energy? More substituted alkene, right? So they're saying the more substituted alkene. Where have you seen in the past more substituted alkenes being the thermodynamic product, perhaps without really discussing it, right? The alkene is more stable in one instance. Yeah, so elimination, Zaitsev's rule, right? We saw that in the absence of steric demands, that in many ways would lead to the kinetic product. You effectively increase the barrier to go to the thermodynamic product, thus allowing the kinetic product. So again, we could discuss a lot within kinetics versus thermodynamics. But yeah, it's in the Zaitsev's rule, right? It's that the more stable alkene forms. And again, in many instances, that's not really a situation where, that's kind of an instance where the energy barrier happens to also be the kinetic product as well, so it's sort of the kinetic or thermodynamic. And what you do when you put a bulkier base there is you kind of allow for there to be a kinetic product, which happens to be the less substituted. So again, we can discuss that later on. But yeah, in this case, you have this alkene. Again, that's why it's important that anytime you learn something new, you relate it hopefully to something that you've seen in the past, so you both refresh on what you've seen in the past, and you know this. So exactly, so more substituted alkenes we've seen as more stable. Thus, at least it serves to reason, right? You can make an argument, which is what a lot of organic chemistry is simply making arguments based upon what we know. You'd make the argument that this is the more stable, and you could say it's because it's more substituted alkene. And you might be right, and you might be wrong, but it turns out that you're right in this instance, so this would be the thermodynamic. Now, where this gets, where I don't like, I sort of taught this way last semester, and then as I started thinking about it a little bit more, I wasn't totally comfortable with teaching this second point as well, because I think it's sometimes difficult to be able to predict the kinetic product. Certainly there are instances where we could rationalize why something might be the kinetic product. But in this case, right, the sort of, and I think the unfortunate simplification leading to more confusion type things that the book will sometimes do is basically say, okay, well, this is the thermodynamics, so this must be the kinetic, right? And the reason might be why. Yeah. So but it's a resonance form, right? So then I think that's kind of what the book is kind of hinting at, right? Is that what you have here is you have a carbocation. Again, this is a resonance form. It exists more like this. But the comment that's being made is that this carbocation, right, has more carbocation character at this carbon. Yeah. And so perhaps due to electrostatic interactions, right, it might be lower barrier to form this product. So that's a good way to sort of look at it. Another way I think is sometimes, but you have to be able to calculate that, right? You'd have to need some way to be able to rationalize that. In this case, I think that that's a reasonable answer that you gave there. But again, in terms of getting at what that transition state is, can sometimes be difficult. But I think that's a good rational answer. And so again, in this case, it so happens that it's a kinetic product. But again, but I think there ends up being some interpretation issues sometimes, right? Because what if what we had was, say, for example, a molecule like that, where we put the additional alkene on there, right? Now they're both secondary, right? And, you know, so again, I guess the important point with kinetic and thermodynamic and sort of thinking about these is really asking the question, can I provide a reasonable argument why it's a thermodynamic? And can I make a reasonable argument why it might be the kinetic? Because I think this is the thing with organic chemistry. If I sat up here and told you that we were, you know, able to predict everything that happened, it's a lie. Again, we try to rationalize things as best as we can, predict things as best as we can, and provide an argument about it. So, but again, I think the important points for thermodynamics is that you recognize that what the thermodynamic argument is, if it's a thermodynamic product, it's going to be the lower in energy. So if you can make a rational argument of possible products forming, that this would be the lower in energy, right? As long as it's rooted in things that you've learned and that make sense at the chemical level, that's good, right? From a kinetics argument standpoint, I think it's perhaps a little bit more difficult because you have to start thinking about the transition state barrier. But if you can make an argument, and a good argument, like was just made, then I think that's fine as well. But it can be a little bit more difficult to predict the kinetic argument. But again, I just want you guys to be able to reason this in that extent. One more point about these is that there's a new sort of term that we'll hear sometimes associated to the two different types of additions across, say, for example, alkenes. And I'll still get to the question that somebody asked me earlier in a moment to sort of follow up on this. But what we have here is two different types of addition. So there's going to be a term that we're going to use for these two different types of addition. It's actually similar. We've heard this in the past. We've heard it in the past in terms of sort of alpha beta unsaturated carbonyl systems, right? So you can sort of see this, the grouping here, right? And if we talked about this in the past, if you have, say, some type of a metal alkyl group, right? It's like a cuprate, right? The cuprate right? We can think about this as being, you know, we call this sometimes let's say, for example, a copper, perhaps like a cuprate counterion, if you want to sort of think about it this way. But we call this what? We call it a 1,4 addition, right? Right? Because part of it's ending up with this carbon, the other part's ending up sort of 4 atoms away, right? Whereas if we add 1,2 into this, what we're referring to is something like a methyl Grignard, where we're reacting directly into that carbonyl, and again, it's right, we're adding into that carbonyl, and so this is what we would call 1,2 addition. And so when we talk about alkenes, we see this exact same nomenclature again, right? So as you might imagine, the top case, right, that would be 1,2. Right, so it's very, see the parallel that we've drawn down here, right? That the counterion ends up here, the methyl group ends up here, whereas in this one they end up 1, 2, 3, 4. We call it 1,4, and that's very similar to what we saw in terms of 1,4 addition into an alpha beta unsaturated carbonyl. So that's a terminology that I think, you know, how you sort of reason that name to help make sense to you. It's just something that we'll see. And again, and then the question will be, well, what if I added at this position? What would that be called, you think? Yeah, 1,6. Exactly. So this would be 1,2, be 1,4, be 1,6, right? So going on and on and on. But again, that's all that it really means is sort of where you're adding. It's either 2 atoms apart, 4 atoms apart, 6 atoms apart. And you see it in a couple different sort of contexts. Yes?
Why are the atoms born
I was just trying to explain, I was just kind of trying to show, it'll probably go right up the oxygen, right? But the point was that there's some counterion. I was trying to draw the parallel, but yeah, sorry if that confused you. So it'd go there, and now it's an anion. We can think about it as an anion bond. It's actually not like that, but I'm just trying to sort of show that they're sort of adding, in a way, 1,4. Okay? The book discusses another class of 1,4 additions, and somebody asked a question earlier, and I told him that I would sort of mention it. And that's if you get to, and say, add bromine across. Again, we have lots of things that we can imagine adding across this, and someone sort of asked me the question, when you add bromine, right, we can imagine getting a couple different forms as well. But in this case, right, what we have is the bromine atom here, and I think the question that was asked was, right, if we draw the parallel from before, right, we can get this. Guess I'll go in the other direction here. You guys could probably draw that mechanism where you draw the resonance form. And so in one case it would be 1,2 addition, one case it would be 1,4, yeah. So that was the question that was asked. So let's get into that. So the question that was asked was exactly what was just brought up, was saying in the case of the bromine, right, there's ammonium ion, right? And so what this actually may exist as, and this was the question that somebody was asking earlier. Okay, so bromonium ion, I guess perhaps a few of you thought this, and the question that was brought up to me was, well, if it goes to bromonium ion, why would I ever go here, right? Because they would look at this and they would say, well, here's a structure here, and I think that's a stabilizing factor, and so perhaps to have to open this up, right, now I would have this carbocation, and maybe now you can't sort of stabilize that carbocation to bromine, so it sort of throws a, perhaps, chink in this. But does it? Yeah. Yeah. Exactly. So again, as we sort of saw before, perhaps a way that we could sort of think about this. So previously we kind of had you can almost think about it expanding out a little bit in terms of where that carbocation is going to end up. You can think about that charge spread out over both this carbon, and this bromide, right, through some sort of resonance form. Because that's really what the bromonium is, right? It's sort of a resonance form, in a way, right? It's a sigma bond, so it's kind of weird thinking about it that way, but it's still kind of resonance form. You're just moving electrons between the two. Generally, we think of resonance forms as pi bonds, but certainly you could think about them in terms of sigma bonds as well. What was just brought up was, well, if it looks like this, the idea still remains that what my atomic compound looks like is delta plus here, delta plus here, and you know, if you want to think about that spread, I guess as I have drawn, it's a whole and positive charge. But again, if we think back to what I was just explaining, we might have a delta plus here. And so as was sort of stated, you could sort of think about this as a Michael-like addition, right? In that there's actually a different term to this. Right, and so the idea is, could you add that way? Can you add through the alkene, right? Because if you look at this sort of structure over here, right, we have the delta positive here, so if it attacks, then we'll just set up the opening in much the same way as a conjugate addition to an alpha beta unsaturated carbonyl. It turns out that this has a name, okay? If I were to add the bromide here, what kind of reaction is that? Here's 1, 2. Yeah. What's that? It's an addition. What are reactions that we normally think of as additions? There's a name for them. And it rhymes with... Rubstitution. Yeah, I don't know. Substitution. Yeah. So it's a substitution reaction, right? And so among the substitution reactions, is it be an SN1 as is drawn or an SN2? As is drawn. It would be an SN2, right? This is an SN2. Why? Because we're making and breaking at the same time, right? And again, we know that SN2 reactions, there's a stereochemical outcome associated with them, right? And so in this case, what I've shown is a substitution reaction. We know that in the case of bromine formation, there is stereochemical integrity involved within this. And it turns out that this is an SN2. This one over here, this is an SN2. This is also an SN2, but it's like called SN2 prime. So there are instances where you have this a lot. So SN2, SN2. But yeah, so it would be called SN2 prime. Okay, so the general idea here is that it's a conjugate addition like in nature, where your leaving group instead of the carbonyl is breaking a pi bond. In this case, you're actually breaking a sigma bond. Okay. Yes. That would be a good exam question. Well, okay. Yeah. All right. Let's think about this. I'm trying to think about it. I'm not sure that it's relevant in the question that I just laid out. And so you're putting me on the spot to come up with a question, because there definitely is stereochemical integrity there. So let's think about it, right? So in that case, it didn't really matter because there was no stereochemistry to sort of start with. And in the case of a bromine and bromination, it's really not all that relevant, in part because, say for example, if you wanted to add bromine across here, all right, hold on. No, I think we could do it. Wait, no, because yeah, I think there would be. There wouldn't even be diastereoselectivity. I was thinking more enantioselectivity, but I think there could be diastereoselectivity to this. And I'm certainly thinking here a little bit on the fly, but let's think about this a little bit, right? If the bromine's going to attack here, right, it's going to be through a specific face. And the product over here, as I drew here, it doesn't really matter because there's no stereochemistry being generated here. There's no stereochemistry being generated here. But in cases where you would have, say, for example, two stereoisomers, and again, I don't know which one would form, but maybe we can think about it together, right? There would be two stereocenters forming. And so we could imagine a product right, and then you have the enantiomers of both of them, right? But well, actually, one of them's meso, which is another question for you guys. But anyway, so we have sort of two, at least, products on the surface, two diastereomers of one another that you can imagine forming. And in truth, there probably is a stereochemical component to this, in part because of the fact that it's an SM2 reaction. And I'll try to give a very, because I don't know the answer here, so I'm bordering on perhaps misinformation, but let's try it for a second. So in the case of a and we're going to spend too much time doing this. But if you were to add into this system, right, the sigma star, again, I'm not really drawing the orbitals necessarily 100% correct here, but where these orbitals need to come in is over here, right? Right? They need to come from the back side just as before, right? And so if we're attacking from that face, then where do you think the bromide's coming from? Right? Because in principle, if this is going this way, then what you have is this sort of pi star in that way. So you put me on a spot there, and so I don't want to go too much into it because I'm nervous that I might make a mistake, but there would be some type of orbital alignment issue that we would have to draw out based upon the lowest energy intermediate. So yes, but let's not worry about it right now. But we could talk about it upstairs for sure. We could sketch this out and discuss it, and I can look up and do it more for you. But yeah, because of the fact that it's sort of would be an ordered transition state, then you would have to consider where the electron's dumping into this orbital and what effect would that have on where the pi star would be that you would donate into over here. And I'm pretty sure that would come from the top face. So anyways, that's yes, but I'm not prepared to discuss it beyond that superficial explanation there. But you see what I'm saying? Everything would be happening simultaneously, so there would be that stereochemistry involved. All right. Perhaps you can try to predict that and come by. All right, so that's. I want you guys to know thermodynamic and kinetic control. I want you to know, sort of understand the molecular orbitals from Diels-Alder, and those are the two things. And now from here on out, what I discuss, you won't be responsible for the upcoming exam. In part because you have a lot of other stuff to, I think, learn and catch up on and everything else like that. And what we're about to introduce is one of these things that requires a lot of practice. And so I want you guys to have that time to practice this stuff. And this involves what we'll discuss through the remainder of today's class, and this is pericyclic reactions. And again, the focus, I'm going to teach you guys these reactions, but the focus that I want to have on this section, and I think this is a fantastic opportunity to really think about diastereoselectivity in more complex reactions, okay, with a focus on stereoselectivity. Okay? And we're going to learn two classes of reactions that we're going to discuss within these. And the first one is going to be, we touched on it already. This is going to be the Diels-Alder. Okay? The Diels-Alder reaction is going to be Diels-Alder reaction we already sort of discussed is going to be basically that 4 plus 2 reaction. Right, we're making those bonds, okay? Now, as you can imagine, we'll discuss this depending upon groups you have here, here, oops. Depending upon groups you have here, here, here. At each of these positions, right, we are now potentially having right, each of those positions offers the opportunity perhaps to have a stereogenic center, right? Depending upon how everything's set up, right, you can imagine any sort of number of different stereoselectivity within here, okay? And so we'll discuss some of the parameters that drive those. The other reaction that we're going to discuss are going to be sort of fewer names depending upon the ones that we want to do. But these reactions are going to be called, this one that I've shown right here is a, they call it 1,4. Whatever the names are. Make sure I get the name right. So we have a Cope rearrangement, we have a Claisen rearrangement. I just want to make sure that I give you guys the... Yeah, so it's going to be a 3,3 sigmatropic rearrangement. And we'll see examples of this where, again, say for example, if you have a heteroatom in there, what ends up happening, even if you don't have a heteroatom in there, okay, so it's going to be a 3,3 sigmatropic rearrangement. Formally what it is it's becomes in a way 3, the sort of name comes from the fact that you can sort of, I'll explain where the name comes from in a moment. Let me just draw it. The name comes from the fact that if you sort of dissect this molecule, kind of what you have is it's really 3 atoms and 3 atoms. And you can sort of imagine splitting them, put a negative charge on one, put a positive charge on the other, and start thinking about the resonance forms associated with these, right? Because this is the bond that I formally just broke. You can imagine the resonance form over here, right? And you can imagine the resonance form over here, right? And so we think about the resonance forms associated with those. And then simply those form together. So in this case, what you're going to see, right, is you've got, say, for example, groups here, A, say B, and over here, again, this reaction is reversible, C, perhaps D, right? And so what you're going to have is perhaps EZ olefins associated with here, and you're going to have stereochemistry associated with here. So again, you see that throughout this process, because those could be cis or trans, these could be cis or trans, these could be back in the same phase and the opposite phase. So there's a lot of potential groups on here that can end up in different sort of transformations. And so we're going to discuss this one as well. So we'll start with Diels-Alder, probably spend about 20 minutes or so, half hour on Diels-Alder. And then we'll move on to this. I'm imagining we'll probably have to go into next class discussing this as well. But we'll discuss, it's worth sort of looking ahead to these two at this point, okay? All right, so let's start with the Diels-Alder reaction. Okay, so in the Diels-Alder reaction, we'll get to the stereochemistry in a moment, but as we just sort of discussed earlier, what this reaction is basically a diene, right, reacting with an alkene. And when we were discussing sort of homo-lumo of these two, we were saying how the sort of homo of one's going to react with the lumo of the other, or vice versa, right? And so in principle, this is a very new reaction to you guys, but we can kind of think about it a little bit as being one of them being a nucleophile, right, and one of them being, say, for example, an electrophile, right? One of them is going to be an electron acceptor, right, like an electrophile, and one of them is going to be an electron donor, similar to a nucleophile. And so anytime you have a system, right, where you have an electrophile and a nucleophile, you can imagine that by attenuating the electronics of these systems, you can either make a nucleophile a better nucleophile, or you can make an electrophile a better electrophile, okay? And so classic examples of Diels-Alder chemistry, you know, if I were to give you this one right here, this is a very high thermal reactive process. You have to perhaps heat it to 200 degrees Celsius simply to get this to go. So it's very, 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 very high in energy. However, in general, as we begin to start changing the electronics of these, the classic, what we sort of consider normal electron demand which I think is normal simply because it's like one of the first. We normally think about this as the LUMO, and this is the HOMO, okay? So we generally think of this as the nucleophile, and we think about this as the electrophile. And so if we want to make the LUMO lower, if we want to make it a better electrophile, what can we do to it? We want to give it more electrons or take away electrons. If we want it to be accepting electrons, we would take them away, right? And so if you want a better electrophile, if you want this to be lower in energy, if you want it to be more accepting of electrons more generally, then what you're going to do is you're going to try to pull the electrons away from that system. And so you can do things like, say, for example, put a carbonyl there. So this is methyl vinyl ketone. Oops. I have to use the perfect pattern right there. Right? So you could have a system where there's your product, and it turns out that instead of this taking place at 200 degrees, you can actually go much lower. Right? And then you can do the same thing to the alkene, right? Instead of pulling electrons away from it, if you want a better nucleophile, then you'll add electron density to that system, right? And so you can imagine adding things to this compound, such as two methyl groups. Again, as you sort of think about that stabilizing the carbocation character to this, this is going to increase the electronics around this. And in fact, this will take place spontaneously. This will take place at room temperature. Okay. Now, that's just to show the point that dienes, when it's more electronically rich, these are some numbers to sort of illustrate that when you have a more electronically rich diene with a more electronically poor alkene, at least for normal electron demand Diels-Alders, you can actually do this at room temperature. Is there like a video?
Yeah.
Okay, so get to stereochemistry in a minute, but there's another, I think, element in here that's important to recognize as well. And so we'll take this one here. I purposely made this molecule symmetric, right? Which led us to really have only one possible product. Okay, but if instead of having the two methyl groups there, I only had a single one, now we've got a problem. Or not a problem, but it becomes a little bit more complicated, I should say. Right? So if we ran a reaction like this, we really have two products that we could form in this case, right? The one would be with the methyl group in that position. The other one would be if I just rotated this the other way, right? Same thing, it's not. Okay, so we've got two possible products from this reaction, just depending upon the approach of this molecule. And so, again, this is the same thing. I'm not implying it's a different reaction. It's the same reaction, just so careful when you're writing that down. So I'll erase this for now. But the question becomes, this is actually this is called regioselectivity. So we talked about diastereoselectivity in terms of stereocenter. This is regioselectivity. So this is kind of similar to, is it a 1,4 addition or is it a 1,2 addition? Right? This is what we call regioselectivity. And so for the Diels-Alder, there is regioselectivity to this. And what we have to start to think about in this molecule is how would this form, and more importantly, because this will move forward once we start talking about a lot of other chemistry, how do we rationalize which one we would expect to form? Okay? And so formally, anytime you're doing this type of chemistry, it's oftentimes good to think about where the sort of electronics rests in the overall system, right? And so and what I mean by that is where is the delta positive, where is the delta negative, match up the charges, and we should be good, right? And so let's just start with this alphabet unsaturated alkene here. And ask ourselves, is this delta positive and this delta minus? Or is it the other way around? And in this case, we certainly have some previous examples that we can sort of build upon, where even if you don't necessarily understand it, you might have seen instances in the past which might guide you in the right direction. But let's sort of talk about, even if we didn't know these things, how do we sort of think about this a little bit? So if we were to look at these two components, how many of you guys think it would be this one here? See, one or two hands. How about this one here? Yeah, so I saw more hands for over here. So why do you think it would be this one here? So wait, first of all, because I know what you're going to say, why would you think this one here? Well, that would actually be bad. So let's think about the two resonance forms, full-blown resonance forms. And the question becomes, which resonance form is better? Right, so we can just draw the two resonance forms, push the electrons onto one carbon, push them onto the other. And if we look at this compound here, what I thought you were going to say is, oh, the carbocations on the more substituted alkene, right? So you might say, yeah, it's going to be this one. But there's something else which you were also bringing up, which actually perhaps makes this bad. And that's what? So that's that this is next to a carbonyl that already has a delta positive here. So even though this is secondary, right, it's still adjacent to that delta positive charge, and that's going to destabilize it. So your intuition of saying more substituted, more stable is correct. However, there's more to this story. And perhaps by looking at the other one, it might make better sense. And why is that? Were you the one? Yeah, you.
Well, my reason was just that it was going to be adjacent to the carbonyl.
Right, which allows you to do what?
Which is just,
Yeah, resonate. Right? In the same way that the positive charge here is bad, that positive charge here is good, right? Because of resonance, because you can actually resonate that up into this molecule. And this is something that we'll see in terms of patterns throughout these systems. Like, oftentimes, again, you guys could probably look at the carbonyl, right? And recognize the carbonyl, the dipole is delta minus, delta positive, right? Delta minus, delta plus. And it turns out, and we'll see this a bit, especially when we start talking about benzene derivatives, but you sort of continue that. So it goes like delta minus, delta plus, delta minus, delta plus. It can sort of keep going in terms of this pattern. You generally don't have a couple delta pluses next to each other. Okay, so anyway, so this would be our delta plus, and this would be our delta minus. And what we want, right, what we want to do is thus find which one has the better sort of delta minus here, right? So as we just said, there's this sort of trend associated with it. So the question becomes, Oh yeah, no, I meant to do the same thing. Because that's the question. I'm not saying this is delta positive and this is delta minus. I'm not saying this is delta positive and delta minus. I'm saying this is what we want. And let's figure out which of these two dienes actually is a better representation of that. Okay? Yeah?
So the top one would be more delta positive on the top of it, closer to a more electron dense point molecule. So the method effect is more necessary.
So
So you don't want to have negative positive.
So the idea here is that you would have a delta positive here. If you're thinking in the right direction, but that's not a delta positive, right? It's not like this is a carbocation that's stable. It's not like that's a stabilizing a carbocation, right? So, but that carbon right there can actually stabilize the carbocation. See what I'm saying? So sometimes it's worth it to just draw the resonance forms, right? So let's draw the resonance forms of each of these. And let's go ahead and let's go with the negative. I think it's quicker that way. So let's draw the delta minus on the bottom, okay? And let's take a look at that resonance form. Okay, so there would be a resonance form. Again, the other potential resonance form would be that sort of would illustrate the electronics of the system. Would be this one here, right? And so that would be, say for example, delta minus here. Let's take a look at the other one. And let's push the electronics here. Right, and so here's all of our potential resonance forms. So here's our resonance forms of the one delta minus delta plus, right? And here's the other one up here. Right? And what do you guys notice about the possible resonance forms that these each have? Which is a better collection of resonance, if you will? Is this a better collection of resonance? Or is this a better collection of resonance? The top one. Why? Yeah, tertiary carbocation. Does everybody see that? Let that sink in a little bit. Right? I basically have done all the possible resonances of the two going in the opposite direction. I've tried to explain where the delta minus, because again, these are the same molecules. We're really just asking, is this delta minus or is this delta minus? Right? And so we're drawing the two resonance forms that would say, for example, put the minus charge here and the positive charge here, and vice versa. And we're comparing them and seeing which one seems to be a better representation of it. And again, as you sort of pointed out, here's some of the resonance forms here. This one has a carbocation at that tertiary carbon. Can't do the same thing here. Try to push the electrons around, you'll see you can't necessarily have that same stabilizing effect. Okay? So, in fact, it's the one that's going to have the delta minus here, and the delta plus here. Okay? And when you look at these two, right, you see that this is not going to match. Right? You want the negative charge, you want the positive charge, and vice versa. So this is not going to happen. You have to rotate around. Right, so you have a delta positive, delta minus, delta minus, delta positive. Right, and so the product that we're going to end up getting is going to be this one right here. Does that make sense? This is something that is going to take a little bit of time. Hopefully it'll make more sense. This is another reason why I wanted to save this for the next exam, because this is going to be very similar to what we discussed when we begin to talk about regiochemistry and benzene derivations, in terms of where's the delta minus and delta plus in benzene derivatives. So we'll have to think about this quite a bit. So I guess when I said diester selectivity, kind of glanced over regioselectivity, but certainly that's something that's perhaps a little bit new to you guys, and it's something that we'll want to sort of think about. So, oh my God. Okay, I'm not going to get to 3-3 signature. So again, start thinking about regiochemistry a little bit. But the other aspect that we want to get to is stereoselectivity, diastereoselectivity. kind of what I said at the beginning. And in some cases, it's kind of, there's a few different positions that we could imagine these groups on. And so I think it's best to think about this. I don't want to overcomplicate this. So we're really going to ask this in two ways, I think. The first is, how does the stereochemistry of the diene translate to chemistry of the products? And how does the stereochemistry of the alkene translate to the stereochemistry of the products? Okay, so let's start with the alkene. Okay, and so if we're going to put A, B, C, D around there, and really what we're going to ask the question here is, when this reaction takes place, where are these groups going to end up in the product? Right, and the question is, which ones are coming towards you, which ones are coming away from you? And the answer for this one's actually fairly simple. And the reason comes down to the fact that this reaction, there's a big parallel here between, say, for example, Diels-Alder chemistry and, say, for example, syn dihydroxylations, right? When you have a reaction that's taking place across the bonds, then the stereochemistry that's over here is going to be effectively maintained. And so the D and B, which are on the same side in the alkene, are going to be on the same side of the molecule in the product, and vice versa. And so I'll explain that in a minute, but you can sort of see that I could have had these going back, but the important point is that they're going the same direction. Okay, so the A and C are on the same side of this molecule. They're going to be on the same side in the product. The B and D are on the same side here. The B and D are going to be on the same side in the product. And the reason, again, just comes down to the fact that this is a process that is concerted. Okay? And so everything's going to happen at the same time, so you don't allow for these two to flip-flop, right? Everything's going to take place at the same component, right? You can imagine this similar to how I drew it here, if you want. Right, so when it forms, these bonds are going to form. Right, and this alkene can come from the top or the bottom. Again, I just happen to draw it in this way. So the product that I have here, if we flip this up, you can see that the B and the D would be on the same side. But again, it could come from the opposite face as well, and you simply get the opposite stereochemistry. Okay? And so given the fact that it's sort of conserved in nature, right, the next question would sort of come down to, what about stereochemistry at the diene? Okay? And in the case of the diene, it gets a little confusing when you try to look at both of them, but certainly you can, but I think it's best beginning to at least think of them differently. And so again, they stay on the same side. The case of the diene, we'll do some symmetry here to sort of help us out a little bit, okay? So the A and the A, what are those in terms of the alkene, corresponding to the alkene? What is that? Trans, right? That's trans, right? Same thing here. That's trans as well, right? So the A's are kind of trans, the B's are cis, okay? And if we do the same thing that I did down here, we react this with the old alkene, right? Question is, what's going to be the relationship between these? And this one's a little bit tougher, I think, to sometimes sort of see. But again, we'll go ahead and we'll draw this diagram as I did over here. And again, then when we sort of draw it in this fashion, hopefully we can sort of see what the net result is of all of these. And so, again, drawing in 3 dimensions is something that I really want you guys to start working on, because again, it makes things easier, right? I think that drawing and thinking about these things in 3 dimensions can be a big hurdle early on, and some people really struggle with it, and so you end up creating rules to try to simplify it, and then you never work on it. But really make an effort to try to draw these molecules in 3 dimensions, see them, and at the beginning it's going to be really hard. This is one of the reasons why I wanted to give you guys lots and lots of practice, so it's not going to be on this next exam. But really practice on it a lot, and then a lot of the other things will start becoming easier. Like, if you can see the molecules in 3 dimensions, if you can do and see where everything ends up based upon drawing in 3 dimensions, then it should be a little bit easier to sort of see. Okay? So in this case, we're going to do a reaction, right, where we're going to form these bonds. And let's think about, right, again, the inside ones are going to be B, the outside ones are going to be A. And what we're going to ask the question of is, what's the relationship to them in the product? Okay? So when this reaction forms, right, where are the A's going to be? They're going to be, these are going to sort of be coming toward you. And the A's are going to be going back. See that? So you can think about it as sort of attacking, right, where you're making this bond, right, is from the bottom. So maybe up and back is bad, maybe out and in, right? So if you think about these, first is coming towards you. Draw this a little better for you. Instead of jumping right to the relaxed state, sometimes it's just best to think incremental steps, right? The B's are coming towards us, are inside of the ring. The A's are coming outside. So let's not try to take the straight leap. Let's just draw it with the B's going in and the A's coming out. Right? So the A's are going out. Now if I relax this, right? If I relax this, what's going to happen? What's going to be coming up, right? If I bend this out, if I relax the system, right? The B's are coming in. If I relax them, the B's are going to start coming up. Exactly. So when we open this up and relax it, so I've shown them in the middle to make it hard, or sorry, to just sort of make it easier to see, but then when we sort of relax the system, we bring these out, both B's are going to be coming towards you guys. Right? And so in this case, what's happening is the B's are coming towards us. The A's are going back. B's are coming towards you. A's are going back. Okay? So you can do a couple things here, right? You could either just try to memorize this stereochemistry and say, if I've got any groups that are trans are going to be on the same face, any groups that are cis are going to be on the same face, and you're not going to be able to sort of work it all on this, or you can just try to rationalize it yourself by drawing the transition states. And so I will on occasion ask you guys to actually draw these transition states to actually see it, just because I tell you guys that this course can often be a bit of an art course. But again, I want you guys to sort of see these two aspects, work on drawing it this way, work on trying to see it. If you have to get a model set to sort of help you, you can do that as well. But really start working on this, start working on this. Okay, and I'll let you guys go.